Finish going through the law of inertia, Newton's first law. An object at rest wants to stay at rest until acted upon by an unbalanced force. An object in motion wants to stay in motion in a straight line at a constant speed until acted upon by an unbalanced force. It's sometimes called the law of inertia. We could also call it, although this isn't really a name that's commonly referred to, we could also call it the law of equilibrium, right? Do you see the significance of that, right? If an object is in equilibrium and it's at rest, it will stay at rest. If an object is in equilibrium and it's in motion, it will stay in motion at a constant speed until acted upon by an unbalanced force. We could also call it the law of balanced forces, even though that's not really an official name for it either, right? If the forces are balanced, if it's in equilibrium, it will either stay at rest or keep moving at a constant speed in a straight line. Now we're going to talk about Newton's second law. The second law, okay, does relate to the first law, but it's not going to seem like it on the surface when I give it to you. That's going to come a little bit later. Newton's second law talks about the acceleration of an object. So the first law talks about the equilibrium, right, when the forces are balanced. The second law talks about when the forces aren't balanced. The first law talks about when an object is at rest or moving at a constant speed. The second law talks about when the object is accelerating because of those unbalanced forces. We're going to say for the second law that the acceleration of an object is directly related to the net force. Directly related to the net force. That means as the net force goes up, the acceleration goes up. As the net force goes down, the acceleration goes down. And that should make some sense to us, right? You push on something harder, how does that affect the acceleration? It's more. You push on something with a less force, how does that affect the acceleration? It doesn't accelerate as much. The bigger the acceleration, the bigger the net force, the bigger the acceleration. Now, it's also in the same direction as the net force. So if I push on something to the right, the acceleration will be to the right. If I push on something upward, the acceleration is upward. Oh, wait a second. I think I just found one that contradicts that. Listen carefully. The object is falling. The object is falling, hits the ground, and comes to a stop. The net force is upward on that, right? As it comes to a stop, the force is upward. Otherwise, it wouldn't stop, right? Isn't the acceleration still downward, though, because it's moving downward? No, the acceleration would be upward there in the direction of the net force, right? Because you get a positive acceleration because it's slowing down in the negative direction. The acceleration will be proportional to the force and in the same direction. Now, how is the acceleration dependent upon mass? The more mass something has, the more inertia it has, right? Listen carefully, the more mass something has, the more inertia it has. The more inertia it has, the harder it is to change its motion. So, the more mass something has, the harder it is to change its motion. The more mass something has, that would be the higher or lower acceleration. Higher mass, higher inertia, right? Harder to change its motion. Is that going to be more or less acceleration? Less. If it's harder to change its motion, it's less acceleration, right? So the bigger the mass, the smaller the acceleration. Make sense? We're going to say the acceleration is inversely related. Inversely related to the mass of the object. So as force goes up, acceleration goes up. But as mass goes up, acceleration goes down. Inversely related, yeah. In other words, the acceleration is equal to the net force over the mass. You can see in this equation, if you increase the force, the acceleration will also increase. Double the force, double the acceleration. Triple the force, triple the acceleration. But if you increase the mass, because it's a denominator on the bottom of the equation, then the acceleration will go down. Double the mass, the acceleration is cut in half. triple the mass, the acceleration is 1/3 of what it was. So the acceleration is directly related to the force and in the same direction, and is inversely related to the mass. Now, I'll be honest with you, most times you don't see Newton's second law written this way. Most times you see it written this way. F is equal to m times a, but it means the same thing. We don't usually write this, but know that F in that equation, F is equal to m times a, or a is equal to F over m, is the net force. So if there's three forces acting on an object, we have to add them together and then use that number in that equation. Here's an example, example number 1 that we're going to use to illustrate Newton's second law. It says, what is the acceleration of a 20 kilogram box if a net force of 50 newtons is applied on it? This is not in equilibrium, right? If it was in equilibrium, the forces would be balanced and the net force would be 0. The acceleration would be 0. If it's in equilibrium, it's going to keep doing what it's doing, right? Stay at rest or stay moving at a constant speed. This is not in equilibrium. There is a net force. There could be 3 forces that add up to give me 50. I don't know what's caused this 50. Okay, whether it's just one force or whether it's 50 forces. Doesn't matter. We're told the net force is 50 newtons. We want to know the acceleration of this box. So this ends up being a pretty straightforward question. This is, if you think about it, quite clearly a Group B problem. Group B involves acceleration, right? So all of those equations that we learned in our Group B last unit, they're still applicable. We're not going to use any of them here though, right? Well, the one we're going to use is our newest Group B equation, which is F is equal to m times a. Okay, that's a Group B equation as well, right? Because it involves acceleration. Let's write down our givens. My mass is 20 kilograms. My net force is 50.0 newtons. We're looking for the acceleration. Let's go to our list of Group B equations, go to the last one, because that's the one that fits the best, and say A is equal to F over m. The net force divided by the mass. 50 newtons divided by 20 kilograms. Now remember what we said here over the last few weeks? Today is the day where what starts counting? Significant figures. So we're going to be even more conscious of that as we're doing example questions now, so that when it comes quiz time or test time, hopefully you nail it. 50 divided by 20 is 2.5. How many digits should it be? Look at our, if we look at this, that's how many digits? This is 3, 2 and 3. Final answer should be the least precise piece of data, which is 2. So we're going to leave it as 2.5. And the units, of course, would be meters per second squared. Now, what's the direction of it? I don't really know. It's the same direction as the net force. So if we say the net force is positive, the acceleration is positive. If whatever direction that is, right? It's the positive direction. Let's take a look at the second one, which is a little trickier, but still doable, I think. It says a 1,200 kilogram car accelerates from rest to a speed of 20 meters per second in a time of 10 seconds. What force is required? What net force, I should say, is required to accomplish this? This is not a Newton's first law problem. Okay, mathematically, we don't even deal with Newton's first law, right? But certainly this car is not in equilibrium. It's accelerating. It's not in equilibrium. The forces are not balanced. It's not going at a constant speed or remaining at rest. This is a Group B problem, right? It involves acceleration. Group A, V equals d over t, would be for when it's in equilibrium. Group B, when it's accelerating, is for when it's not in equilibrium. Let's write down some givens and then determine which Group B equation we're going to use. Say mass is 1,200 kilograms. I'm going to say my time interval is 10.0 seconds. What else do I have? This 20 meters per second is a V. What V is that? VI or VF? Blake? VF, good. Blake, what is VI? Do we know that? Yep, because it starts at rest, right? Good. And we're looking for the net force. the net force required to do this. You've got a list of 6 group B equations now, 6 of them, counting the one that we did today. F is equal to m times a. Which one do you want to try? And let me preface that by saying you can't really try the wrong one. There's not a wrong one to try if you pick group B, right? So pick a group B equation. Which one do you want to try first? Yep. A is equal to delta V over delta T? Absolutely. Absolutely, you can try that first. In fact, I think that's going to definitely be one that we use. The one that I'm going to do first, just the way that my mind works, is this. I'm looking for net force, right? I only have one equation with net force, right? So let's try that. Let's try F is equal to m times A. And then I realize, as I sub my numbers into that, I don't have the acceleration. Well, that's fine. Now, Nick, now that's the time that I'm going to try A is equal to delta V over delta T. If you do it the other way around, find A is equal to delta V over delta T, and then try F is equal to m times A, is there a difference, really? No, it doesn't matter what order you do it first, right? This is just the way that I think. If I'm looking for F, then I'm going to use F is equal to m times A, and then just try to get whatever else I need to sub into there. So it's a two-stager. Delta V is VF minus VI, 20 meters per second minus 0. My time interval is 10 seconds. That gives me an acceleration of 2.00 meters per second squared, which I'm going to turn around and sub into here. And get a value of 2,400 newtons. 2,400 newtons. Now, where do I round this to in terms of significant figures? This is how many digits? 4. Zeros at the end of a number count. Zeros at the beginning don't count. So that's 4 digits. This is 2. This is 3. Final answer should be 2 digits, right? That means 2,400. I'm going to have to put it in scientific notation, right? 2.400 times 10 to the 3. We want it in 2 digits. So let's underline our first 2 digits and then put a little arrow on our third. The third is a 0, which means that we're going to round 5 or more, we round up. 4 or less, we round down. That's a 0. We're going to round down. So it's 2.4 times 10 to the 3. If we said let's say it was 2458, 2.458, the third digit would be a 5. Then we would round the 4 up. It would become a 5, 2.5 times 10 to the 3. All right, I'm going to have you guys work on a few questions here on worksheet number 10. Now, pay close attention here to which ones that I want you to work on, okay? Worksheet number 10. Question number 1, 2, 3, 4, 5, 6, and 7.